All right, questions? So the ODP is posted, and I gave you 2 days on it because I think there's going to be questions, and I think people won't start it until later today. So, but it's doing Fibonacci's recursively, but you have to cache up your results, and you need to use long longs, so you can go up to 90 something for calculating Fibonacci's, and if you don't cache it, it won't finish. So you need to be doing this bit where you make an array that you use to save values that you've calculated, and before you recurse, check that array and see if you've already found the value of whatever number you're after. If not, calculate it recursively, and then before you return, save it in that array. Okay, same thing you're going to be doing with knapsack, same thing we've done with other things. Questions on that? Okay, so yeah, you can have a global array, except that it's got to be global to your function, because you don't get to write the main function. But yeah, so fib of n, and it returns an integer. If n is less than or equal to 1, we just return 1. Otherwise, we use a recursive definition. Okay, so that's standard recursive Fibonacci. Really, really inefficient computationally. So the idea is when we come into the top here, we're going to have some kind of cache, some sort of save array that we initialize to 0. And before we do this recursive step, we're going to say, let's see if we've already calculated this value. So if save n is not equal to 0, then we must have saved a value in there. So let's just return it. Otherwise, do the expensive recursion, but before you return, save it in your array. So you only pay the recursive price once. The next time that we want the same Fibonacci number, right, the nth number, it's already going to be saved. We'll just read it from memory and return it right away. All right, I've also gotten rid of the T and the little t and the A and the question mark options on the assessment program. So your only option is grade and exit.
I like the A.
Yeah. And we're going to see how that works. The reason I've done that is because I'm being kind of hypocritical, because I'm telling you, don't use the assess program to debug your program. Write your own test cases. Make sure your code works, and once you're sure it's working, go ahead and assess it. But then I give you these extra test cases in assess, and I give you hopefully useful feedback from running the tests. And so I'm kind of saying, yeah, but go ahead and try it through a test to see if it works first. And it's mixed messages there. And I really, really want you to write your own test cases. I want you to think of this as like PA 4.5, right, or 4.1. You've got to write a function to do this, and then you're going to give it to me, and I'm going to grade it. Except the me is this automated assessment system, right? So I want to make sure you're getting in the habit and are able to test these things on your own. So when you run them through the assessment system, it'll just give you a thumbs up or thumbs down now. So we'll see how that works. The Fibonacci one is easy to test, right? Because you know how Fibonacci numbers work. And in the README, I gave you some sample numbers, smaller and larger. So you can try your code with that and make sure that it's doing the right thing. All right, let's talk a little more dynamic programming. So let's talk about egg dropping. So engineers are always dropping eggs, right? This is like a classic experiment. Usually you try to build some contraption so you can drop an egg and it survives, and you try to make it so that you can drop it from the highest height possible. So egg dropping, here's the question. You have a building with a certain number of floors. Okay, so let's say it's got F floors labeled 1, 2, 3, all the way up to floor F. And you have a certain number of eggs. So you have F floors, and let's say you have E eggs. And what you want to know is what's the highest floor that you can drop an egg from without it breaking? Okay, what's the highest floor you can drop it out the window and it does not break, it survives? And there's some simplifying rules here. So all of the eggs are identical to each other. The eggs are perfect, meaning that if you drop an egg from this floor and it survives, you can drop it from any lower floor and it will also survive. On the other hand, if you drop it from this floor and it breaks, then had you dropped it from any higher floor, it would also have broken. So they behave perfectly. And if you drop an egg and it survives, you can use that egg again, and it's not damaged at all by that drop. So there's no penalty for having dropped this egg 50 times as long as it hasn't broken. Okay, it'll act the same each time that you drop it until it breaks. Once it breaks, you have to throw it away or eat it or something. So you can only use it until it breaks. So the question is, for a certain number of floors and a certain number of eggs, how many experiments do you need to conduct in order to answer this question? What's the highest floor from which you can drop it safely? And your answer might be 0. It might be that when you drop it from the first floor, it breaks. Or it might be that you can drop it from the highest floor, F, and it still survives. Or it could be any floor in between. So if I say there's 16 floors and you have 1 egg, how many experiments, what can you guarantee me, right? I want you to say, okay, I only need this many experiments to answer your question. 16, why? There's 16 floors. You've got to test them in sequential increasing order. If we only have 1 egg and we drop it from the second floor and it breaks, we haven't answered our question because we don't know if it would have survived from the first floor or not. So the only way we can do this with 1 egg is first drop it from the first floor, then the second, then the third. Now it may break at the 3rd floor and it only took us 3 experiments, but it's possible it would take us 16 experiments and it would survive each of those, and then we could say, okay, the 16th floor was the highest we could drop it from. So with 1 egg, the answer is pretty straightforward. So let's make a function egg. And this is going to be equal to F if your number of eggs is equal to 1. It's equal to 0 if your number of floors is 0 or somehow negative. Yeah, basement floor. That underground building. And if you have only 1 floor, it's going to take you exactly 1 experiment, no matter how many eggs you have. So what if I give you 16 floors and 2 eggs? We know we can do this with 16 experiments, but can we do better? 9 experiments? So how do we do that?
Well, it could be as cool as, oh, okay, so since you have 2 eggs, you can drop at every other floor. So once it does break, we tested the floor below.
Okay.
If it breaks there too, then the
That's pretty cool. So we could drop every other floor all the way up to 16. In worst case, let's say it breaks at 16.
Well, it would be, if it breaks at 16, you have to test the floor below it in that case.
Right.
You dropped it at 14 last, so that would be a total of 9.
Okay, so that's a total of 9. So F equals 16, egg equals 2, 9 experiments. That sounds pretty good. Can we do any better than that? Start in the middle. What? Well, close to the middle then. We could try a high-low program, right? We could start with floor 8.
Yeah, you could do a high-low up until you have 1 egg left, and then do everything.
Okay.
Everything that you have covered, because that would drop this 9 to an 8.
The interesting thing is, though, there's a penalty to this high-low game, right? Which is you lose an egg if you guess wrong.
Start in the middle, drop it, and then go to the first floor, second, third, fourth.
Okay. So we drop it from the 8th floor, and it breaks. Now you got 1 egg left. We can't subdivide anymore. We got to go back to floor 1, try 1, 2, 3, 4, 5, 6, 7.
Exactly.
Which is still 8.
But that brings us down to 8.
Yeah.
Cool. And if we get lucky and it survives from floor 8, now we've only got floors 9 through 16 to test, and we still have 2 eggs. So we'll end up, you know, in a better situation there. But worst case, this is going to be 8. Cool. Can we do better than 8? So start at 4.
So that would do a better average case. But I think wouldn't that be a worst case?
So what's the worst case here? If it breaks at 4, we're down to 1 egg, and we have to do 1, 2, 3 experiments.
Yeah, it's the same like with 8.
Breaks at
Then you still
16.
only have, well, if it
breaks at 16, then you just do.
but if it breaks at 8, now you have to go all the way back up.
Oh, no, you have a good point. Yeah. So it would be way less.
Well, if we try it at 4 first, and it survives, then we've got 2 eggs, and we've only got to do floors 5 through 16. So we could split that in the middle, and then depending on whether it survives or not, we might have to go every floor from 5 up to the midpoint. But we can definitely do better than 8 that way.
Yeah, that would be,
So what if you have 76 floors and you have 7 eggs, right? It's going to be really, really confusing sort of how to do this. But we're already developing an algorithm for this in this discussion, right? Depending on what the first floor is that we drop an egg from, different things might happen, depending on whether the egg breaks or survives. And we could try this experiment for every possible first floor. What if our first egg is dropped from floor 5, right? If it breaks, then we have to do potentially 4 more experiments, so that's 6. But if it survives, we have 2 eggs, and we have fewer floors we have to check with our 2 eggs. So is there a sweet spot? And we could do this thought experiment for every possible initial floor. It definitely, maybe. I think it's a little more involved than that. But I think that's the order of it, definitely.
I'm thinking like you would drop it from an arbitrary small, bigger than 0 amount.
Mm-hmm.
Would be a good start, I think. And then if it breaks, you do 1, 2, 3.
Mm-hmm.
If it doesn't break, you just do it for the next tower.
Okay.
And so you can make this kind of recursive. You would jump 4, then 4th above, and try it again.
So what kind of algorithm are you describing?
It's recursive,
It's recursive.
but
Say again?
it sounds very similar to what you said, yeah.
Yeah.
I'm not sure why you would choose 4 specifically. Why not halfway?
Why not? Well, we don't know. But what we're describing here is a case of repeated subcases, right? We can express the solution to this problem. We can express this function in terms of other values of this function, right? So we've got a few base cases here, but let's look at the general case, F floors and E eggs. Well, we can try this experiment of dropping the first egg from every possible floor. So we could say for I equals 1 to F. And we're going to drop an egg from that floor, so that's one experiment, okay, dropping from floor I. And there's two possibilities, the egg survives or the egg breaks. Okay, if the egg breaks, then we have one fewer egg, and we know that the correct answer was somewhere between 1 and I minus 1. So the question is, how many experiments do we need if we have E minus 1 eggs and I minus 1 floors? Well, that's just egg of I minus 1, comma, E minus 1. That's the number of experiments to answer the question with our remaining eggs, plus the one experiment we did dropping the egg from floor I.
And that's if we decide to do each individual floor because we have one egg.
This is saying, suppose we started with our first drop from floor I, right? That's one experiment. And if it breaks, now we're going to have E minus 1 eggs, but we know that it can't survive from floor I or above. It can only survive between floors 1 and I minus 1. So we're solving the same question, but with E minus 1 eggs and I minus 1 floors. So however many experiments it takes to answer this, we add one more. That's the total number of experiments if we drop from floor I for our first egg and it breaks. Left and right subtree. If it survives, then we still have all of our eggs, and we know that it survived from floor I, so the critical floor is somewhere between I plus 1 and F. So there's a total of F minus I floors we have to consider using E eggs. And so this is the number of eggs in that case. And we're looking for the worst case scenario, so we want the maximum of these two values. That's the guaranteed maximum number of experiments we need if we start with floor I. So we want to find the best floor to start with, so set something like best equals however many floors, because we know that's our worst case. So this equals max. If this is less than best, set best equal to this. That's the end of our loop. Return best. And that's a straight dynamic programming implementation of the algorithm. I did. We didn't. Right? But this expression of the number of required experiments in terms of other smaller experiments, if we write that into code, it will eventually give us back a number that says what's the guaranteed number of experiments that will suffice to answer this.
Oh boy, wouldn't it be great if we knew exactly which floors to drop the egg?
That would be. And that's a separate question. All right, so here's some egg drop code. And we're going to get rid of this nasty caching of results initially. So I'm just going to prompt for number of floors, number of eggs, read those into floors and eggs, and then call our egg function and print out the answer. And the egg function is really not too bad. So it just fits on one screen. So if the number of eggs is 1, then we need number of floors experiments. Okay, that was one of our base cases. If the number of floors is less than or equal to 0, we require no experiments. That's our second base case. If the number of floors is 1, we require 1 experiment, regardless of how many eggs. You just need to know if it survives from the first floor or not. So there's our 3 base cases. We'll put in the caching later on, but for now we're not going to cache any results, so that if won't have any effect. So here's our best results so far. Here's a loop. I switched around the variables on you, so F is the floor we're trying to drop from. Floors is the number of floors. So if the egg breaks, we now have to check floors 1 through F minus 1. and we have eggs minus 1 total eggs. So this function tells us the best number of experiments plus the one experiment we just did that broke our egg. That's the number of total experiments we need if the egg breaks. If the egg survives, we now have to interrogate floors f plus 1 through the top floor. So that's total of floors minus f floors, and we still have all of our eggs. And this gives us the number of experiments we need plus 1 for the experiment we just did. So we want the worst case of those, right? Because we're looking for a guarantee. What's the number of experiments that will suffice? So if break is larger, then break's the worst case. Otherwise, no break's the worst case, and I call that this. And then we're just trying to minimize the number of experiments we need. So if that's a better answer, we'll record that, and we'll return that as the value of our eggs. So let's say 7 floors and 1 egg takes 7 drops. That's a base case. 7 floors and 2 eggs takes 4 drops. And every time that we call the egg function, I'm printing out what the arguments are, number of eggs, number of floors, and what the answer was. And you can see we're starting to see some reuse of subcases. All right, let's do 16 floors and 2 eggs. And let's see what our best answer was. 6 drops.
Are you choosing a random number for what floor it breaks?
No, we don't actually know what floor it breaks. We're considering all the possibilities, right? So when we drop an egg, we're looking at 2 possibilities. It breaks from this floor or it doesn't. And that's giving us a bifurcation of our search tree. So in our tree are all the possible scenarios. This particular branch might correspond to this is the magic floor where it breaks. But we're actually not saving any information about what the actual floor is. And that's a harder thing to do because unless we pick a floor, right, we can't say what the right, how to actually run the experiment. It would depend on whether it breaks or not. But we could modify this, I believe, and use this in tandem with actually dropping eggs, and it would tell us, okay, now go to this floor, now go to that floor.
So, are you doing like 7 searches and 6 searches kind of?
Depends on how many eggs you have. So if it's 1, you're looking for every single one. And if there's like 3 or 4, you're looking for the first one.
Okay, so you do 7 with 1 and 7 with 6 with 2.
So we did.
That looks like a lot more than that.
So let's try this again. So 16 and 2 eggs. So the first thing it did was it said, suppose we drop from the 2nd floor and we have 2 eggs, right? We can answer this question. Suppose we have 2 floors and we have 2 eggs. We can answer this question with 2 experiments. And it was using that to answer the question, what if we have 3 floors and 2 eggs? And it was using that to answer the question, what if we have 4 floors and 2 eggs? What if we have 5 floors and 2 eggs? Or 6 floors and 2 eggs? And it's trying to get to the answer of 16 floors and 2 eggs. But let's see if we can draw this out. So 6 floors and 2 eggs. Well, to answer that question, we need to know 2 things. We need to know how many experiments it takes if we have 5 floors and 1 egg. And we need to know how many floors it takes if we have, this gets really tricky to write out. So we're doing a loop. So we're going to set I equal to 0. So we're going to ask for egg 0, 1. And I is equal to 1. We're going to ask for, this is actually negative 1, 0, 1, 1, 1. Yeah, we have a base case in there for negatives. All the way up to 5, 1. And then we have, and these are going to be interleaved. I'm not showing them in the same order that they're going to actually be executed, but we're also going to ask the question of 5, 2, 4, 2, 3, 2, 2, 2, 1, 2, and 0, 2. So just the first level of recursion, we're actually looking at 13 different subcases, right? So these cases correspond to where the egg breaks in our first experiment. Okay, this is the experiment of dropping from the first floor. This is dropping from the second, the third, the fourth, and so on. And if it breaks, then this will be the number of experiments we need to finish answering the question, right, plus the one experiment. If it survives, then we have to solve these subproblems and find which one gives us our answer. So it's a different feeling from like knapsack, right, where we're actually solving a particular problem. We're exploring the space of all possible problems, all possible scenarios where the critical floor sits, and we're trying to find the worst case number of experiments we need. So it's a different feeling to the problem overall, but it's the same use of these recurring subcases. It's the same way of expressing the value of this function in terms of the value of that function evaluated at different arguments. And in this case, the arguments are always getting smaller or staying the same, which means if we trace this out, eventually we'll get down to a case where either the number of floors is 0 or 1, or the number of eggs is 1. And those are our base cases. So 16 floors and 2 eggs takes 16,385 calls to the egg function to answer the question. Unless you turn your cache back on. So 100 floors and 7 eggs, and I don't know if that'll actually finish. That's probably a little too intense. Let's try 30 floors and 5 eggs. I'll give it half a minute. So it's some ridiculous amount of recursion. But it's because, you know, with 30 floors, our first set of experiments are going to be on the order of 60 subcases we have to explore. So imagine a 60-way tree. And the depth is roughly the number of floors that you have. So 60 to the 60th, something like that. It's pretty ridiculous. So let's just try 16 floors and 3 eggs. There we go, 131,000. 16 floors and 4 eggs, 500,000 calls. And if we want to actually see the solution, so there's 16.3, takes 5 drops. 16 with 4 eggs, still takes 5 drops. 16 with 6 eggs, still 5 drops. I don't know, I haven't tried that. I'm not sure what the function looks like for like how this varies with E. All right, so let's put back in our caching of results. So we have a save array. So number of floors, number of eggs, all initialized to 0. When we come in to our egg function, we're going to check that save array. And if it's non-zero, we're going to assume that's the answer for that particular set of arguments, and we'll just return it. And at the end, before we return the best value, we'll save it in our array. So we add that one line of code in. And 16 floors and 5 eggs, so 5 drops. And so 100 floors with 7 eggs, 7 drops. 100 floors with 10 eggs, still 7 drops. I don't know if we can get better than that. 100 floors with 100 eggs, 7 drops. So that's probably your best case, because if you have more eggs, it's not going to help you. So 16 floors, you're going to have 5 experiments no matter how many eggs you have. So that's another example of dynamic programming. Okay, like I say, a different feeling, but breaking a problem into smaller versions of itself. Okay, just like knapsack, just like rod cutting, just like Fibonacci.
Can we go back to the, like, what are we exactly doing just kind of still can't catch?
For which part of this?
Like when you just did the cache part.
Oh, the caching?
Yeah.
Okay.
Not equal to 0.
Good. So this is what takes all the time, right? Because we're looping through and we're calling egg recursively twice inside here. So this is expensive. But once we come out of this loop, we've got our answer. Okay, we found the best number of experiments. What we're doing is we're saving that in this array. So indexed by the number of floors and the number of eggs we were asked to analyze, we're saving that answer, okay, which is going to be positive, right? So the next time, if we happen to call egg with the exact same number of floors and number of eggs, we've already saved it in the array, and we know that because we're going to check that entry in the array, see that it's not 0, so we must have changed it. So this must be the answer to what the egg function is, so we just return it. And it short circuits all of this. Okay, and that's what you're going to do in Fibonacci and in the ODP. Same procedure. Mm-hmm.
The best case, if you have the right number of eggs, is floor log base 2 plus 1.
Yeah, that seems reasonable. So if you have enough eggs, 127 floors takes 7. 128 eggs takes 8. Cool. So it is logarithmic. Very nice. Yeah, and it's still pretty slow.
There's a lot of things to check. 200
Yeah.
At least we get to see an answer this one.
That's right. Yeah, it seems to be log 2. Excellent. All right, other questions on that? All right, well, moving on. So let's talk about sorting. So sorting, right, is this classic problem. You have a set of data and you want to organize it in some sort of order. And the only real assumption here is there is an ordering, meaning that any two things in your set of data can be compared to each other, and we can determine what the relative order of them is. Now, for numbers, we just think about greater than or less than. Which number is greater than which number? Okay, but for strings, we could alphabetize. We could use string compare to say lexicographically which one comes first, which one comes second. But as long as you have an ordering on the elements of your set, we can sort them. Okay, from smallest to largest or largest to smallest. So what's the first sort we usually deal with? Good old bubble sort. And bubble sort's usually my go-to sort. It's not great, but it works. So I don't know how well this is going to work. I was going to bring in playing cards and I forgot. So you get post-it notes instead. You have playing cards with you? Do we want to ask? Do we want to ask why you have playing cards with you? Cool. All right, yeah, I'll take your playing cards. That'll work better. Cool, thank you.
People ask me why I dropped
Now you know. It's an educational. All right, so we're going to pick on diamonds because we're computer scientists, so we're going to be rich. All right, so we have a set of cards. And we want to order these from smallest to largest. Okay, here's the idea. So here's the data in your array, and we want to sort these so that smallest comes out on the top and largest comes out on the bottom. So the idea of a bubble sort is we make a series of passes through your data. We examine your data from beginning to end multiple times. And each time that we do this, the goal is to take the largest object or the heaviest object and have it sink down to the bottom to the right position that it should be in. And while we're doing this, the smaller values, the lighter ones, tend to like bubble up to the top, okay, like air bubbles, bubble sort. So we could do this very directly by simply going through and figuring out what the largest element is, right? Start off with the first one, and if the second one's bigger, remember that's the biggest. And do that until you get to the end. And then when you found that this was the biggest number, go ahead and move it down here to the biggest position. Okay, that's even more inefficient though. So the way bubble sort works, we compare each number to the number after it, and we make sure those two numbers are in the right position relative to each other. So we'll compare the first number with the second, and if the first number is smaller, everything's fine, nothing to do. Compare the second to the third. If the second number is smaller, fine, nothing to do. If the third number happens to be bigger than the fourth number though, we're going to swap them. And we're going to keep going. We're going to compare the new fourth number to the fifth, and if those are in the wrong order, we're going to swap them. And if this is smaller than the sixth number, we don't have to do anything. And after we've gone from the beginning to the end, we're guaranteed the largest number is going to be in this last spot. Okay, so how does this work with actual data? So 6 and 4, those are in the wrong order. Let's swap them. 6 and 2, those are in the wrong order. Swap those. 6 and 8, those are in the correct order. 8 and 5, those are in the wrong order. Swap them. 8 and 10, those are correct. 10 and 3, wrong order. Swap them. 10 and 9, wrong order. Swap. 10 and 7, wrong. Swap. 10 and 1, wrong. Swap. And we're done. And there's your 10 in the last position. If we do that exact same thing again, what's going to happen? You're going to get the second largest, right? So 4 and 2, swap them. Now this doesn't affect the second largest one, but this is how we avoid having to do this more than once per pass. So 4 and 2, swap them. 4 and 6, that's fine. 6 and 5, swap. 6 and 8, that's fine. 8 and 3, swap. 8 and 9, fine. 9 and 7, swap. 9 and 1, swap. 9 and 10, fine. And there's your two biggest. So how does this look in code? Yeah, so let's say we want to sort n numbers, so they're sitting in an array. We're going to have to do a total of n passes like this, because each pass puts one number into its correct spot at the end of the array, towards the end of the array. We have n numbers, we're going to have to do this n times worst case. So we can just go for pass equals 1 to n, and inside here, move largest number to correct spot. Right, the remaining largest number that we haven't already moved to the correct spot. And this requires us to go through all the elements in the array, compare each element to the number after it. So for I equals 1 to n, if wrong order, swap. So very, very rough estimate. How many times potentially are we doing this stuff in terms of n? Rough estimate, n squared. But you can do better than that. So how do we do better? No recursion. We're in bubble sort land, so we're in 121, so not too much recursion yet.
But I know what you could do with recursion.
How would you?
You'd go through it.
Mm-hmm.
Well, no, side of the array. You go through it, dig up to the very end. You recall a function, so you can take the array size minus 1. So it's going to go all the way to the array, but not the greatest.
Oh, cool. Okay.
You keep doing that until you're at the very top, the smallest.
Okay.
And that's where you stop.
So bubble sort of n things, make a single pass, swap through to get the largest thing in place, and then bubble sort your same array but with only n minus 1 elements. Cool. That's nice. That should work. It's still going to be n squared though, more or less.
You could be better, but not.
Yeah.
Could you cut that down by saving into an array where the data values are, and then you can check for cases like you went 10-9 at the end of that last part example, so you can check to see if it's already.
You could. So you can start analyzing the data and possibly eliminating some of these passes.
Oh yeah, so it's like top.
So you could do some housekeeping. If you did this recursively, even if you unroll it, right? What's happening when you make a pass? You're moving the largest number into the correct position at the end. And what you're observing with this recursive idea is that the second pass does not have to go through all n entries. It only has to sort n minus 1 entries. And after you've moved the largest value from this n minus 1 array into the correct spot, your next pass only has to go through n minus 2 entries. So instead of n squared, if we use the smarter version, we're actually going to need this many operations on this inner pass, right? It slowly goes from n down to 2. And so the total number of operations require something like this. And do we know a formula for this?
Oh, yes, we do.
Yeah.
It's n choose 2.
Yes. It's n choose 2. Let's throw an extra 1 on the end.
Oh, right, n choose 2 minus 1.
Right. And it's also n times, I think it's n plus 1 over 2, which is n squared over 2 plus n over 2. But this is actually the same thing as order n squared. So
Like, even though if you had something that was just n squared would be less, it's still n squared.
So here's the thing with orders of complexity. They're kind of taken in the limit as n gets towards infinity. Okay, so if n is very small, there's certainly a big difference between this and this. Right, 5 squared versus 12.5 plus 2.5, that's a big difference. But if n is really big, if n is like a trillion, right, the percentage difference between this and this is very, very small. Because a trillion squared is so much bigger than a trillion over 2. And the factor down here where we're dividing by 2 has no effect on the growth of your complexity, right? Order n squared, if you double n, you quadruple this value n squared. N squared over 2, if you double n, you quadruple the value of n squared over 2.
So, kind of similar to like, it's kind of a mix between saving as an array and the recursive. Could you not only, could you record both the smallest value and the largest value in your first pass, and then basically increment one of those and decrement the other in order to get a smaller?
Come from both ends.
From both,
Yeah, that should work.
have the work you need to do.
That should work, and that would cut your work in half, which means order-wise it'll still be n squared. But there's a lot of wiggle room among order n squared algorithms, right? So that might be twice as fast as something else. But in terms of order of complexity, it's considered the same. And it's similar to the question of suppose we get a faster computer. Suppose this CPU runs 10 times as fast as that one. Our bubble sort will certainly run 10 times quicker, but the penalty in doubling the size of our data will still be 4x. The penalty in making 3 times as much data will still be 9x. Okay, and that's the only thing that this order of complexity is really trying to grasp. So it's not looking at bare computation time, which is why we can throw away these constant factors. In fact, if we had an algorithm and it turned out to be something that took order of complexity 100,000 n squared, that's still order n squared. Now your n has to get much bigger before this 100,000 becomes irrelevant to you. But eventually, as n gets towards infinity, this becomes a complete non-issue because your performance is dominated by this term. So yeah, there's some cool embellishments we can make on a bubble sort. Doesn't help the order of efficiency, but it increases the performance overall. Another thing we can do, and this is really easy to do, remember we're moving through the array and we're comparing each entry to the number after it. Anytime that we swap 2 entries, we can just set a flag. And if we get to the end and our flag's not set, we know we're done. The array is already sorted. And usually it's going to end up being sorted before you've gone through your last pass, unless it's really pathological. So we might be able to cut this short, and even though we're saying let's do a total of n passes, at some point we might get down here and find our flag's not set and say, okay, break out of the outer loop. We're done. So that's another embellishment. All right, so bubble sort, order n squared. So what we'll talk about tomorrow are 2 other n squared sorts, insertion sort and selection sort, which playing cards definitely help with. So I'll try to bring mine in tomorrow, but if not, I might hit you up again. So we'll talk about insertion and selection sort tomorrow, and then we'll talk about merge sort, radix sort, heap sort, and quick sort. And then we'll be all sorted out. All right, I'll see you tomorrow.